Hello everyone and welcome to the new video. So in this one I'm going to tackle a problem of early detection of melanoma, which is skin cancer. And melanoma is a very deadly cancer, but most of the cases can be cured if we can do an early detection. So in this video I'm just going to show you how you can easily build a deep learning model to for early detection of melanoma. So we will be using PyTorch, and for any model we need some data. So let's see. A recent Kaggle competition has some data that we might be able to use. So it's called melanoma classification, SIM, ISIC, and um, it has images of skin lesions, so different regions of skin, and we will be using that to kind of build a model to predict whether it has melanoma or not. So you can see that the images are provided in DICOM format, which is fine, and they have also provided some images, same images in JPEG format. So what we are going to do, so there's a lot of other information about the patient, and you can probably try to improve on this model by using these information. They are quite helpful, assuming. So let's see that there is one CSV file called train.csv, which has image name, patient ID, approx age, okay, and some more information, and a target column, so 32,500 zeros and only 584 are ones. Wow. So you see that it's quite skewed. So the first guess that comes to our mind is using area under the rock curve as a metric to evaluate models on this. So yeah, I mean, out of 33,000 cases, only 580 have melanoma, and rest they don't. And okay, so we have to build a model. So if you want to see what these images look like, I mean, yeah, it's difficult to look at some of these images, but I can show you some. So let's see. Okay, so this is one of the image, and yeah, so there are different types of images, and so you also have some kind of scale here in some images you don't. So yeah, so these are our images in simple words, and each image is associated with a target variable, which is binary, 0 or 1, and that's what we have to predict. We have to predict the probability of an image from the test set having melanoma or not. If we look at the evaluation of this one, evaluation, okay, area under the rock curve. So as we guessed, it's the wise choice, and now we can try to start building a model on this data. So first of all, you need to download the dataset. It's quite huge, so 108 gigabytes of data. Yeah, that's a lot of data. And the next thing that you want to do is do some kind of stratified split. Now there are only 580 samples in the whole dataset which have melanoma. So what you want to do is probably do 10 folds, but I'm going to show you only 5 folds. So you can probably try doing 10 folds, and maybe that gives you better results. But even 5 folds is quite okay, I think. So first file that I create is called createfolds.py. You can also do it on your own, but I'm going to show you nonetheless. So in this file we read the training.csv. So import pandas, and then we split the training.csv into 5 different parts using one new column. import pandas as PD, and you have from model selection. Okay, let's do this one. So from sklearn import model selection. So I hope the text is visible. Okay, so now I create a main function, and inside this I'm going to read the data. So I have df period.read CSV. My data is located at a different location, so I will say workspace workspace can do like, I cannot copy this. Okay, can say input path is workspace. Okay, and we can also do import OS to join the path. So now we pd.read CSV. Read CSV takes a path, so we do os.path.join, and then we have input path comma train.csv. So that's all, and then it's going to read your training data. So the next thing that you do is, you create a new column df kfold and fill it a value of -1. It's okay. Now what I'm doing here is just shuffling the dataset, the CSV file, reset index, and so I have a new shuffled data frame, and then I get the target values. So df dot target dot values, and then I can have model selection stratified kfold. So I can do n splits equal to 5. You can use 10. Why stratified? Because we want the ratio of positive to negative samples in every fold to be constant, to be the same. And now we have we can do for fold comma train idx test idx or valid idx, whatever, and enumerate, and then you define x. What is x? X is your data frame, and since you have stratified kfold, you also need y. Okay, so this will be not just enumerate but kf dot split, kf dot split, and inside this enumerate. Okay, now there's this few things that you don't need. Don't need this one, don't need this one, and now you can do df dot lock all rows, and kfold column goes with fold underscore. So we just add a number of fold number to the column, and now you can save the new data frame. So you can do df dot to csv. Where do I want to save it? So I can do the same input path comma train underscore folds dot csv, and we don't need the index to keep it same as the original data frame. So now let's run this code and see what happens. Hopefully it works. So I'll go to my terminal, and I have create folds, and boom, it works. So now if you go and see the file that has been created, I'm not going to do that. That file has a new column called kfold, which has values from 0 to 4. We can also create 10 folds. Let's create 10 folds. Doesn't matter. And just replace the file. Okay, now what we are going to do is create our first model. And today we are going to do it a little bit differently. So let's see. I hope you like it. So let's see what we have here. And we create a new file called main.py. And inside this file, you will have your model, you will have everything related to training. So we might need a few things, like we might need OS for joining path probably. And okay, one more thing that I missed is you need to resize the data set. So images are of really different sizes, and some images are too huge, and it's going to take a lot of time for you to train the model if you don't resize them to one single size each. So you have to resize them. How to resize them, I can show you if you want. So let's write a function called new Python script resize images. And what this will do, I'm not going to run this one because I've already resized the images. I've also published a kernel on Kaggle if you want to take a look there, or probably I can just show you there. So let's see. Let's see. I can just show you here. Okay, I'll let it open. So what we will do is we will use PIL Python library, and we will read the image and then we resize it to a given size. So now you can choose your size what you want, like 224, 224, 512, 512. The bigger the size, probably the better your results are going to be. So if you do 1024 cross 1024, probably you will get a much better result. But I tried with 224, so we are also going to use 224. This Kaggle is taking a long time. Okay, anyways, so I will show you when that's ready, hopefully soon. Let's wait for a few minutes. Okay, so here it is. And okay, so let's see what I'm doing here. Very simple. You create one function to resize one image. You have one image, resize one image, just one function. So I take the image path, then I extract the last bit of the not the bit but last part of the image path, which is something.jpg, and which is my base name. So I can do that using os.path.basename. So that will extract the file name or the base name. Then I have a output folder. And then I create an output path. So output path should be output folder plus base name. So then I read the image using PIL and I resize it to a given size, and then I save it to the out path, which is really very simple. Now why we do it like this, because there's one thing that you can do. You can parallelize it. You can parallelize it, and then it's going to be super fast. So what we do is we have the input folder, okay, with all the training images. We have the output folder, which is empty for now. You have images, so I use glob to create a list of all the images inside the training folder, input folder, and then I use joblib parallel. I create a certain number of jobs, and then I call this function resize image function with different arguments for each image. And now in Kaggle kernel, it's going to take you to time, so better use your own local machine to do all this conversion. It's going to be super fast. Took me like 10 minutes, and otherwise it's going to take you 1.5 hours. So yeah, you can do it. You can probably do it yourself. I'm going to show you the cool part. So I'm going to remove this file, and we have the main. So the main function, we need a few things, like we probably need OS, you probably need Torch, you probably need NumPy and pandas. Okay, so you have all these things, and now you can create your first basic model. So let's say we are not here to reinvent the wheel, so we are going to use one of the pre-trained models. So which pre-trained model you want to use? So let's say we want to use ResNext. So I'm gonna create a class, and x 50 32D 32x 4D. Okay, so that's my model class, and this inherits from torch.nn.module. So let's also import that. Import torch.nn as nn. Okay, so we got this one. Awesome. And now we have a init function, serve comma pre-trained equal to ImageNet. So we say if pre-trained is ImageNet, then load the pre-trained weights. Need to find super, and it's going to be same as the name of the class, then self and underscore init. Okay, so now you can create a base model. I will just say self.model is I'm gonna use pre-trained models. So import pre-trained models, and then we have pre-trained models, and you can get the SE ResNext 50x 5032D 32x4D. So SE ResNext 50 32 underscore, no, there's no underscore x4D. So I mean, I can just go here and see. Can I? Okay, let's see res, and I need this one. Okay, let me close this one. Okay, so I can just copy this, and that's my model. Okay, and I can do pre-train. It's copying all the training data for me from somewhere, I don't know. And I can say pre-trained equal to pre-trained. So if my pre-trained is none, then it doesn't load the weights. Okay, so I'm not going to do anything fancy here, but you just have to create another linear layer. So remember that our metric is area under curve, so we don't need to do any kind of sigmoid, softmax kind of thing. We just need to rank the images, and for that we can just use any kind of linear output. So I'm going to do self.out equal to linear, and this has 2048 output, so you can check that. You can just go here, take this part and print it. I can show you. So to import pre-trained models, and I cannot paste in this terminal, so I have to type everything. Pre-trained models dot text, and let's see, press next 50 32 x 40. I hope this works. Yeah, so you have the last linear layer which has 2048 inputs, right? And that's what we have to change now. So we use 2048 inputs and 1 output. Okay. No, sorry, it doesn't work like that. So you have yeah, sometimes I make mistakes. Okay, so it doesn't work like that. I mean, I can obviously just change the last linear layer, but to keep some flexibility, I'm just going to use dot features from the model. So let's see what that looks like. So I go to SERS next here, and it has this set model, and it has a dot features. So it's running it from layer 0, then 1 2 3 4, and then then it returns some features, and we are going to use those features. We are not going to use the outputs. So we also need to change this to adaptive pooling. Okay, let's see what we have. We have the layer 4, and here you see the fully connected from layer 4, not this one but this one. Here it returns 2048 outputs, and that's why we in this one we do 2048, 1, and then we define a forward function. So forward function will take batch of images, first of all self and batch of images, and then we can calculate the batch size, then channel height width is image.shape, and we say okay, now we have our first feature, which is self.model.features, and then there goes the image batch of images. And we have then we need adaptive average pooling, otherwise model size might not be supported. So f dot adaptive torch functional from torch okay, and then we have, did I import it wrong or what? Adaptive, let's see. Oh yeah, from torch.nn import functional as f, and then you have dot adaptive average pool 2D, and then you specify x comma 1, your axis. Now you need to also reshape it to your batch size. So x equal to x dot reshape batch size and -1. So you have that, and you can now pass it through the output layer. So output will be self dot out and x. Okay, and now you can return output. Okay, so now you have your model, right? Now all you have to do is create a um, training script. So you have to create a lot of things, training and engine and dataset and all that stuff. But I've done something that can make your life easy. So um, I'm writing the most used functions and classes in a library called that's fantastic machine learning. And from here you can just import the engine. So the idea is provide the flexibility of PyTorch, so you don't lose anything that's in PyTorch, and just have some helper functions. That's it. So helper functions, I mean, like, you have there are some different types of engines, different types of loggers, different types of data loaders, different utils. So like like that, and then it becomes a little bit easier for us to implement everything in one go. So if you have not seen my previous videos, then go and see them, and I have implemented all of this, and I will show you how I have implemented the engine and data loader here, and which is very nice and it always works. So there are only few things that you need to take care of. Training data path. So we specify some kind of path to training data. So home workspace, input. This part is going to be huge. JPEG train 2 to 4. So I have resized them to size of 2 to 4 cross 2 to 4. You can do that too. Okay, so that's my training data path. So I've created a new function called run, or I can probably just call it train, and that's my path. And now I read the CSV file, or I can just check this one. Read CSV trainfold dot CSV. So this function takes an input argument fold. And now I can define a few things, like we will use GPU, so device is CUDA, and we can define epochs, 50 epochs. Train batch size 32, valid batch size 16. Okay, so we have that, and now we have defined the fold here. So fold is just an integer. So when fold is provided, like when fold is 0, your validation k fold value inside the data frame is 0, and you have to take the validation where k fold is 0 and everything else is training. So df, so we can write like df train or df valid. So df train is df dot k fold not equal to fold, and we just reset index and drop it. Okay, we got this one, and similarly we have df underscore valid, but here this is equal to fold. Okay, now what is the next thing that you do is like you have to um, normalize the images. So for normalization of these models, you have to like take the mean and standard deviation, and then using those normalize RGB values. So let's do that. I specify, I can just do it here. I can specify mean. So for this model, mean is 0.485, 0.456, 0.406, and standard deviation is 0.229. Okay, and to normalize, you can use argumentation library. Simple. So let me just import that. Okay, so I'm going to create an augmentation and using argumentation where it always normalizes. So I'm going to call it train augmentation, because we can have different training and different validation augmentations, right? Compose, and here I'm going to do normalize mean std max pixel value, which will be 255, and always apply to true. So this is my training augmentation, and similarly I have validation augmentation. So it's the same for now. Later it might change. Okay, so we have some training augmentation, we have some validation augmentation, and then we can so now we will use this well, that's fantastic machine learning. So because it already has everything, it has a data loader that we have built previously, so we're just going to use that. So we go to data loader, images loader.py, and here we have a classification loader, which takes two inputs. It takes the path of the image and it takes the target. That's it, and you can use it for any kind of classification, image classification problem. So I'm going to do here from dot image import classification loader. Okay, and now classification loader takes path of image. So train images, we have df train dot image name dot values. I'll just convert it to a list. Okay, probably it's not required to convert it to a list, but let's just do that. So list of images. So train images is my training data path, which is defined. Okay, where is it? Training data path, right? And comma I plus dot jpg. So whatever the image name plus dot jpg for I and train images. So train images, if you have not seen the training data, okay, I can probably show you. So it's train data.csv. So data.csv has a image name, which is the name of the image inside the training folder. So not a big deal there. Image name and target in the end. So that's all we are interested in. So using the image name, we create this list of image paths, and then we have train targets, which is okay. Now similarly what we do is we create validation stuff. So I will take this one, and I will replace everything with valid, but we did one replacement which is not required. So validation images also come from training data path, right? So we have training images, we have validation images, training targets, and validation targets. So now we can create our data loader object. Train dataset is classification loader, and classification loader takes image paths. So my image paths is train paths, train images, sorry, train images, and then it takes targets is train underscore targets. Then it takes resize, which is a tuple, but in this case we have already resized the images, so I'm going to put it none. And augmentations is train aug. Boom, done. So we got classification loader for training dataset, and similarly we have for validation dataset. Let's fix it now. Okay, and now we can create the data loader. So did we import torch? Yeah. So now we create the data loader, and train loader will be torch utils dot data loader, and here you have train dataset, and batch size is train batch size, and shuffle will be true. Num workers, I don't know, 4. Okay, so now you have the valid loader here, and you have to remember that you have to keep shuffle to false here, because we are using this fantastic machine learning library, and it will if you provide shuffle true, then it's not going to return you the targets, so you have to use your own targets that you have created earlier to calculate the score. Any kind of metric loss you can calculate, fine, that's okay. If you're just interested in loss, then you don't need to keep shuffle to false, but we are not just interested in loss. So now we have the model is a serious next pre-trained ImageNet, which is fine, and then we to device, we have the device defined, right? Yes, to model goes to the device CUDA in our case. And now what we do is we specify an optimizer. So nothing really very complicated here, and everything that you have already used. Atom optimizer, and we do model.parameters, and learning rate is, we set the learning rate to be 1e minus 4, and we can also have some kind of scheduler. I'm using reduce learning rate on plateaus. So when it plateaus, reduce the learning rate. So we can use same optimizer. We can use the patience of 3, threshold of 0.01. Let's just remove that. And mode is max. Why is mode max? Because we will be using this scheduler on AUC, so which is the metric of the competition. And we can also have to make things faster, we can use Apex. Now if you don't know about Apex, just use it for now. I'll probably have to make another video to explain Apex. So from apex import amp, it's from NVIDIA. If you don't have it, just skip this part. amp.initialize, because its installation is not very straightforward. It's actually just 2 lines of code, 2 lines to run, but yeah, I'm not going to explain it in this video. So you have model, you have optimizer, and you provide some kind of optimization level. So let's do O1 and make verbose to 0, verbosity to 0. Okay, so apex is used for mixed precision training, so you can train a little bit faster and without occupying a lot of memory. And then we need some more things, like we probably need early stopping. So this library is amazing. It doesn't have a lot of stuff. So whenever I find something interesting, I put here with proper credits and everything. So this is one of the functions, modification of what you have seen probably at several places. Modified it a little bit, and I use this early stopping, so I can just go here and do from .utils import early stopping, and it's same as my previous videos. So yeah, same parameters kind of thing. ES is early stopping, and now we have we can specify some early stopping criteria. So we can stop on reduction of loss. We can also stop on increase in AOC. So whatever, if AOC doesn't increase, we can stop there. So let's do that. So I can do like with a patience of 5. So let's leave some time for scheduler, and mode is again max. Okay, so initialize my early stopping too. So now for epoch, and range of epochs, we train and we validate and we early stop, and then we are done, right? But now the main part comes. So you have to design a function, some kind of engine to train the model for one epoch and also to validate the model for one epoch. So we go back to our fantastic machine learning library, and we see that okay, there is also engine. And if we go to engine, there is a very general engine. Obviously it's not well commented, so what I'm going to show you today, you can use it like that, and you can also try to explore it. If you have any troubles, if you find some bugs, feel free to send a pull request. And so I designed a simple engine which has a data loader, a model, optimizer, and a device. So these are the things that we always need. And it also has a scheduler. Probably sometimes you need a scheduler inside, so which steps after each batch of training, right? But sometimes you need a scheduler which steps after every epoch of training. And you also have accumulation. There is also like, you can use TPU if you want, and FP16 using Apex. So you have everything here. So the only thing that you need to take care of now is how is the data going to the device and how is going to the model. So if you are using, so you can use your own, obviously you can use your own custom data loader. But if you're using a data loader, any custom data loader, so let's see the data loader that we used. I can show you from here. The data loader that we use, the classification loader, looks something like this. It's not very complicated, quite easy. So now what's happening is it's returning two keys in the dictionary, and that's how your keys should look like. So you have these two keys, image and targets, and that's how it should look like in the forward function of the model. So you have image and targets. So even if you're not using it, just keep it there. Now I will explain you the most simple and easy part. So you have the epochs. Now you can, what we can do is let's first import the engine, the general engine from well, that's fantastic machine learning. Engine, import engine. Hey, and now we go here and we say, okay, my training loss. You can see what engine returns. I'm in process of writing some documentation about it, but this is like very general stuff. It has just been made like this so that it's very simple for you. So it returns average loss, and so we have training loss equal to engine dot train, and you have train loader. What did we call it? Train loader or something else? Oh, train loader. Yeah, train loader, and you have model, and you can have a optimizer, and also you already know the device. Rest everything you don't need except for FP16. So you can do FP16 is true. Okay, and that's your training part. Easy, simple, and still customizable. Oh my god, I've seen so many libraries where people do a lot of things which is not even customizable. So I can now do valid loss and predictions, because if I go to the engine, I see that there is also an implementation for evaluate. Not only that, there is also an implementation of predict, okay, which just returns you the final predictions where you don't have to calculate the loss. So evaluate. Now where does a loss come from? It's also very interesting and very simple. So evaluate returns the final predictions, which is an array of floats and losses, and it also, like, if you have one class, then it's one dimensional. It's always two dimensional, but you have only one element, so it can be used for multi-class classification easily. So there is nothing that cannot be used for multi-class classification. So train. Okay, so we got this one, and now we do engine dot evaluate, and we have the same thing. We don't have the FP16 thing, do we? We don't need that, right? Okay, no, we have the TPU thing. Okay, so we got the predictions, we got the valid loss, and now we can calculate the metric. So what we do is we just stack the predictions together. So predictions is a list of lists, right? So final predictions, so we are just calculating all the predictions from model and appending it to final prediction. So final prediction is just going to be a list. So what we can do is we can just stack the list. So predictions is np.v stack, and predictions, and we ravel it because we have only one value, so we just ravel it. And now we calculate AUC. So AUC is metrics dot ROC AUC score. Obviously it doesn't predict because I need sklearn metric from sklearn import metrics. Okay, and you can do here valid targets that you've already designed. That's why shuffle has to be kept false. And predictions, okay, now you got the AUC, and now you can step the scheduler, which is our case, it's reduce LR on plateau. Step, not static but step, AUC, provide the AUC value, and you can print f epoch is epoch and AUC is AUC. Alright, so now you got this. Now you say if es dot early stopping, right? Now if it's early stopping, you just break. But oh crap, okay, this one es AUC dot model, AUC comma model comma path of the model, so you can just do model path. We define it now, we will define it now. So you can just do print early stopping and then you break. Done, everything done, and still very customizable. I don't know how people work, man. Classification loader. Okay, so we are done with the training part, and we have created something using something that we have created before a lot of times. Now we can run it, but we forgot something, model path. So where do we store the model? So model path, so let's store it in the same directory here, this one. I don't know if I'll be allowed to copy it. No, it's going berserk. Okay, deep learning. Okay, so now we have all the training stuff. Let's run it, and run train fold equal to 0. So that's how you can train for fold 0. So now the idea behind like using this train function with a given fold is simple, that you can use arguments, and so you don't have to run for all folds in one command. You can have multiple commands and you can run it, save some memory. But there is one more thing that I forgot to do. So the engine from this library returns, if you look at the code, it returns you see that the model should return something and loss. So that something is actually prediction. So when you go to evaluate, it's using the prediction. In the train mode, it's not using the predictions. So your model here in the forward function should have the same name as the data loader stuff, and now it should also return a loss. So loss here, I can just do BC with logit slots, and we have output, and we also have targets. So now I know that this is going to show some error about the shape, which is fine, and it's also going to throw an error about the types not being consistent. So you can also fix that by just using just converting the type inside here, inside targets dot reshape. No, after targets dot reshape, obviously. So now we can train the model. So just to type as out. Okay. So now it returns an output, and it also returns a loss. Okay, so now let's train it. Python. I hope you're on the same one. Yeah, Python main dot py. It should run fine. That doesn't happen before, obviously. Okay, so I have a problem here. BS. So batch size, the strong typo, but that's okay. Let's see if it runs now. Okay, woo, training, nice. Pretty excited about it. Okay, so let it train, or let's not let it train. And now we write the predict function. Uh, Prediction is also quite easy, so you don't have this much stuff that you have in training. So prediction function is quite simple. um, and what you can do is like, okay, uh, take one fold and make predictions for it and use the same augmentation as you used for validation. So I don't know if I should go there. Okay, let's do that. Let's do prediction part 2. It's not very difficult and it's fun. I'm gonna copy this whole thing, and we create a new function. Just copy the training function, create a new function called predict, and instead of training data path, now I have no, too much. So we don't have training data path anymore. We have test data path, and it changes to test. So you have obviously also changed the test data. I mean, resized test samples. Everything here remains the same. We can say instead of valid batch size, it's now test batch size. We don't need this. We don't need training augmentations. We can call it test augmentation, and we don't need. Oh, we didn't read the CSV file. df is pd.read CSV, so it's the same CSV for test data without the target column, obviously. So you have start.path.join, and no, we don't have the path here, right? Okay, no problem. I can just copy paste this one for now. And just CSV. Okay, so we have the test augmentation, we have test images. So let's change. Yeah, okay, let's change this. Okay, so we have test images come from df underscore test, and I will also include df underscore test target new column equal to 0. Everything is 0. It's a fake target. Everything is fake. So we have test images, we have df test and test images, and not testing data path but test data path, test targets. Test targets of no use, but we need them for classification loader. So you don't actually need to create so many data loaders. It's very simple. And we don't need the train loader, we just need the valid loader. Change the name probably. Test. Everything is test. Shuffle false, number worker 4. We have the model, and now we need to load the model weights. So we can do here, we can write here, we have model path, right? So model path, and where did we save here? Predictions, model path, and model paths is a folder. Oh, okay. So model path should not be just a folder, but path to the model. So model path, comma, model. I will just do like model and folder number. So f dot bin. Okay. So I can just take this one. Okay, and I can what it is model dot to. Then we need to load the model static, model dot load static torch dot load, and path to the model. Okay, that should work. So specify the fold and predict, and it's going to make predictions for that. Okay, so we have that. We don't need optimizer, scheduler, this thing. We don't need early stopping. So we can now just like make prediction. So we don't need all that stuff. And we have the engine from our fantastic machine learning library. Predictions is engine.predict, and you have test loader, model, and device as device. It's just device. It's CUDA. And then you return and p.vstack predictions dot ravel. Okay, so we designed a framework actually. Okay, so now what you can do is this is your model, the SERES Next 50, and you can also like you can change the model here. You can do different kinds of augmentations. So like if you apply some shift scale rotate here to training augmentation, probably also apply some flipping, random flipping. And if you do that, and if you train this model for like 5 or 10 folds, then you will be getting a AUC of around 0.90, which is quite good, quite awesome. Just remember that you don't try to overfit a lot. And AUC of 0.90 means that given one image which has melanoma, and one which doesn't have melanoma, it's 90% that probability we will be able to separate them. So we have built quite a good model in my opinion, and there's also, if you look at the specific competition on Kaggle, then there's a lot more that you can do, because you have the patient info and we have not used the patient info. Just make sure that you see the predict function. I made it really very fast. So you just call here, you can call predict fold equal to 0, and then you have this well, that's fantastic machine learning library, and I'm just putting some nice stuff I find everywhere, like trying to modify and trying to fix things that you have, trying to implement stuff that I've already done. So there's also an example of FRCNN. You can also take a look there and see what's happening. So it's quite good. I don't know if GPU works right now on this one, but I'll see if when I have time I can try to see if TPU works. If it doesn't, I'll fix it. If it doesn't work, you feel free to send a pull request, and you can also install it using pip. So pip install uh, WTFML. Well, that's fantastic machine learning. And now we have built this whole thing, and it's very customizable. You can obviously use your own data loader, but you have a simple classification loader, and you have early stopping, and there is one engine which is already implemented that will work with almost all kinds of data loaders. And it's really very customizable code now, and it's giving a very high AUC value of 0. 0.9, and probably 10. You can improve it much more. You If you use large image sizes like 1024 cross 1024 and some network like efficient, probably you can improve it even further, but I'm not going into details there. So this is my model for now. The model, you have to remember, should return loss. And it's not like now you might say like we cannot use augmentations like mixup. No, we can just implement it here. If you want to add mixup, add it here. You don't have to go to data loader to add anything. And that's all for today. Let me know how was it, how was the um, video, and if there's something that I missed, and if there's something that I can improve, let me know in comments. And also like, subscribe, and share. If you have not subscribed yet, please subscribe now. And share my videos, and see you next time. Thank you very much. Goodbye.